before we can even begin to tackle stoichiometry, we need to understand solubility.
I know exactly what you mean. Let's begin.
I got some regular table salt. Just gonna mix her right in there. Oh, that looks good.
Looks soluble.
Looks soluble.
But doesn't answer our question.
Not yet. What do you got there?
I have honey. It's Centrella since 1917.
Nice.
Flavored with grade A clover. Oh. Not soluble.
No. Well, maybe. It's too viscous.
I don't know. We're saying not soluble.
Alright, next we got Crest whitening toothpaste.
That's not whitening. That's baking soda and peroxide whitening.
Baking soda and peroxide whitening. Just gonna unscrew you right there. Hold on to that.
There we go.
Alright, it's just gonna...
Be careful. That's so much. Yeah. Okay.
Not soluble.
Not even, well, maybe a little bit. Yeah, actually...
This is not answering any questions.
We need to do more.
This is making me more confused.
Oregano.
It floats.
So we know that the density of oregano is less than that of water.
Still not answering our questions.
But we're closer.
Alright, and
We're
finally,
definitely closer.
finally garlic salt.
That's really good. I love garlic salt.
Here, you want some?
Mm. That's soluble.
It's soluble.
What does that taste like? Oh!
Here, let's just mix it up for good measure. Oh, that is some murky water.
It's a little bit soluble. The toothpaste is a little bit soluble.
The toothpaste is soluble, you just have to mix it.
Mix it, yeah. You gotta put energy in. There we go. Some science for you.
Alright.
Okay, so that clearly didn't work. Maybe we need to try ritual sacrifice. For some of us, this is very difficult. This box has been with Joey for 33 years.
33
years. But for a sacrifice to be valuable, the thing being sacrificed needs to be valuable. So, as with all sacrifices, you must have your standard sacrificial blade. Oh, watch out. That's pretty dead. And, of course, as with all sacrificial blades, it can't just be dead. It needs to be sacrificed. Joey, hammer. Sacrificed.
Here's your balanced equation for problem 17. You got your HCl and your BaOH2, and that's going to give you BaCl2 and water. Now when you balance it, you put a 2 right here, and 2 right there.
That looks good to me.
So the next thing we have to do is figure out how many moles we have of each solution. So we have 0.381 molar HCl, and we have 0.0800 liters of that. So you do some multiplication, and you get 0.0304 moles HCl, and since in every HCl molecule is one H plus molecule, it's also 0.0304 moles of H plus. Doing the same thing for the BaOH2, we get that it is 0.0137 moles of that molecule, but since there are 2 OH ions in each of those, you multiply it by 2 to get 0.0275 moles of OH minus. How do we know which of those is in excess? We know we had 0.0304 moles of hydrochloric acid and 0.0137 moles of barium hydroxide. So how do we know which of those is in excess? We know that we have, for every one of these, we have 2 of these because of our mole ratio. And because this is more than double this, we know that we have excess of the HCl, which means we have excess of the H+. Yes.
Yeah.
To figure out how much H+ we had in excess, we have to start with the amount of barium hydroxide that we used and multiply that by the mole ratio to figure out how much HCl we actually used. Doing that simple stoichiometry, we get that we used 0.0275 moles of the hydrochloric acid. If we subtract that from the amount that we started with, we get that we had left over 0.0298 moles of H+, ignoring this number that I wrote down that's incorrect, which means that if we divide that by the total concentration of the solution, which is 0.3130 liters, so we divide 0.0298 divided by 0.3130, we get the molarity of H+ in the entire solution, which is 0.00952 molar H+.